Yes, so welcome to Topics in Knot Theory. We will be talking about combing braids today. I hope, if we'll get there. But I have a few comments before. So first of all, Leonard asked me to repeat a part of the proof of the unique factorization dilemma about unique factorization, and when I was preparing to repeat it, I realized that I made a mistake there. So I owe you a correction. It will not happen today because I want to prepare a cartoon explaining it, so maybe on Friday, maybe early next week. But anyway, homework 10 will be on the web by tomorrow midnight, possibly today. Likely it will simply be prove Markov's theorem. And for that, I wanted to first go through Alexander's theorem once again, and I made a cartoon to explain it. And maybe I was a bit too ambitious about how much I can put in one screen, so I hope you can actually see this cartoon sufficiently well on your screens. Okay? But anyway, let me remind you. So, Cn is the configuration space of n points in the complex plane. So these are z in Cn, so each z has many components, with the additional conditions that zi is not equal to zj if I is not equal to j. So they're all distinct. Cn tilde is this space modulo the permutation group, and the braid group is the fundamental group of Cn tilde, and we talked about it last time that it's actually tangles that always go up. Okay? Alternatively, you can write it with generators and relations, and I write here what are the generators and relations. I will not repeat it. And then, just to emphasize the relevance to knot theory, I stated Alexander's theorem, which says that every knot or link is a braid closure, where a braid closure is you take the braid B and you connect the top strands to the bottom strands in order. And here they're connected by turning to the left, to the right, but equally well I could have turned to the left, or I could turn to the back or to the front. They're all equivalent. Or I could do some strands, well, there's other variants, okay? Anyway, here is the proof of Alexander's theorem made into a cartoon. So you start from a Morse link. A Morse link is a link projected to the plane, but it's actually without modding out by any motions. It's the actual projection to the plane, and with the assumption that the vertical height, let's call it t, or y, you know what, y. The vertical height is a Morse function. So if you've seen Morse functions in differential geometry, what it means is that all critical points, basically there are well-defined maximas and minimas, and these are the only critical points that need to be when you're talking about a curve. Okay? So Morse links are, two Morse links are equivalent if you can get from one to the other by horizontal deformations, and alternatively, horizontal deformations that don't change the combinatorial structure, by Ridermeister 1, 2, and 3, by a cancellation of a pair of a minima and a maxima. So if you have like a squiggle shape, you can straighten it to a line. And finally, by the windshield wiper move shown here. So if you have something crossing under a maxima, you can move it to the other side. Okay? and likewise for minima, and likewise for crossing over. Okay. In a Morse link, every strand is either upgoing or downgoing, and the upgoing and downgoing are meeting in the critical points. I draw the downgoing in red and the upgoing in green. And my purpose is to dominate with green, because in braid closure, almost everything is going up. The only thing that goes down is on the way back. Okay? So my purpose is to dominate with green. So first thing, I rotate all the crossings so that there are no crossings in which red and green meet. So basically, I turn all crossing green by rotating them. So here is a schematic picture of what you get. So first of all, no crossings on red anymore, but you do have crossings in green, as shown here. And you do have all sorts of green strands, and they're all going up, or at least not vertically up, but up. And you also have the red strands, and they look like integral signs because they go from a maxima to a minima and they go down, though they could be inverted integral signs or C symbols or inverted C symbols. Okay? Then comes the fun part. You choose disjoint monotone going up or down, purple paths that takes all the maximas to the top and all the minimas to the bottom, and with no purple or red intersections. So basically you take the first integral sign and you connect it to the top, and you connect its bottom to the bottom. You take the second integral sign, and so on. Now this is always possible because basically because basically because before the things I need to avoid are vertical lines, okay, are topologically, combinatorially vertical lines. If I want to avoid a vertical line with these purple lines, I can just move to it, and I want to go up, I can go up parallel to it, either to the left or to the right. So there is no need to ever, it's always possible to make these connections. However, not uniquely. So, for example, if you have two red lines, one on top of each other, you can connect the bottoms to the bottom and the top to the top, either as shown here or as shown here. Okay? Okay. Once you've done that, once everything is connected to the top and the bottom, you just pull. So the purple lines are really just guides. So you use them to pull the maxima and the minima down up to the top and down to the bottom, while going under everything you might have crossed. So the only things you might have crossed are other green lines, right? So while going everything that you might have crossed, you pull maximas to the top and minima to the bottom, and this is a picture of what it looks like at the end. And if you look at this picture, and it's a schematic picture, you still have to fill in various connections, but if you look at this picture, almost everything is green, meaning going up, and the exception are red strands that go all the way from the top to the bottom. They are behind everything because the original red strands here had no crossings at all, and when I pulled them along purple, I pulled them under. So the red strands are under everything. And they induce the identity permutation because they don't cross each other. But that's exactly a braid closure. This is a braid, well, if you want, slide all the red strands to the right and you'll get this picture, right? Or simply think of them as happening in the back, and you get the back picture of a braid closure. Okay? Now, Suppose, are you with me? Is this clear? It's actually a rather elegant proof, I think. If you want to prove the Markov theorem, so Markov's theorem says that two braids close to the same link if and only if they differ by a certain collection of equivalences, transformations, which I mentioned last time and I don't want to mention again. Okay? But what do you need to show in order to prove it? Well, first of all, okay, or how would you prove it? One way to prove it is as follows. First of all, you show that this procedure is well defined modulus these Markov relations. Of course, it's not well defined because there are all sorts of choices along the way, but you just have to show that it's well defined modulo the Markov relations. And to show that, you just need to show that whenever you change one of these choices, the end result changes by a Markov relation. And it's best to go from right to left. So first you show that if you modify the choice of the purple line by a move like that, this corresponds to a Markov move. Then you show, so then the procedure is well defined from here on. Then you say, if you rotate left or right, it doesn't matter because of Markov moves, and then the procedure is defined from here on. And finally you say this, okay? That actually doesn't yet prove the theorem. It only proves that if two braids are obtained by this procedure from the same link, then they differ by Markov moves. Now I need to show that if two braids produce the same link, they differ by Markov moves. It's a different statement. So all you need to show is that every braid, so every link which looks like a braid closure is obtained from this procedure from some initial point. And I will leave this to you again. Okay. So yeah, that's what I had to say about reviewing last class, and I want to make a few comments and then I want to move on. So comments. So computationally, yes, Leonard.
Oh, sorry. A clarification about the rotating crossings.
Yeah.
How do you rotate the crossings?
I've shown it last time. So if you have a crossing in which you know, the two strands are pointing down, so actually this should have been red according to my conventions, you just rotate it by 180 degrees so it becomes okay, so I rotated it by 180 degrees. I hope I think I've done it right. And now in the crossing, the strands are pointing up, which means that the down strands, which are from here to here, from here to here, and from here to here, and from here to here, are not involved in any crossings. Okay? Anyway, so comments. First of all, I want to emphasize this is a computationally inefficient. So in principle, you can use this to compute knot invariants. You can, find an invariant of braids and verify that it satisfies the Markov moves, and then use it to construct an invariant of knots. And in fact, many knot invariants were first discovered this way, including the Jones polynomial. Okay? This is computationally inefficient. So this is computationally, maybe two L's, inefficient. And the reason is, computing this procedure is easy. Implementing this procedure is, well, it's not so easy to implement this procedure, but in principle it's linear time, or maybe, no, it's quadratic time. I mean, it's not a lengthy computation. However, the resulting braid tends to be a rather long one. So let me explain. So if you have a knot of complexity n, what does complexity n mean? So if you have let me first write this. So if you have a knot of complexity n, the braid it would come from, so the braid this algorithm produces, will be of a higher complexity. And so what do I mean by complexity n? I mean the number of crossings, say. Right? But the number of crossings, but basically all measures of complexity tend to go together. So if the number of crossings is n, you can bound the number of maximas and minimas by some linear function in n. And then you can bound the number of edges by a linear function of n, and therefore the number of red edges and the number of green edges by a linear function of n. So basically here all the features appear roughly n times. Then I connect with purple lines to the top. So I have n integral signs, and each one I connect to the top, and it may cross about n horizontal, or not horizontal, but nearly horizontal green lines. So the bound on the number of crossings that I get is n squared. And each crossing between purple and green here becomes a pair of crossings, in fact, becomes a single braid crossing here. So the braid that you'll get here will have complexity roughly n squared. So a knot of complexity n would come from a braid of complexity n squared, namely n squared crossings. I think I can do better. I think I can actually bound the number of green lines a little better. So in fact, I think I can improve this to n to the 3 over 2. But this is still more than n. So if you have some exponential time algorithm and you run it on the braid as opposed to somehow figuring out to do it directly with the knot, you're likely to lose. Okay? So generally speaking, it's computationally inefficient. So that's my first comment. And my second comment is a bit weird. Oh, sorry, I still have a comment on this comment. I gave you a bound. So, given a knot of complexity n, I don't know how to get a braid of complexity less than n to the 3/2. I actually don't have explicit examples where it is necessary to go up to n to the 3/2. It's possible that there is a better algorithm to change knots into braids that doesn't have this extra cost. So let me call it an open problem. But to be honest, it's really a locally open problem. I mean, I don't know how to do it, but I don't think anybody ever wrote it in a sort of formal way, and I don't think lots of people thought about it, and I don't think, I mean, maybe somebody else knows. Okay, so the locally open problem is find a sequence Kn of n crossing knots such that the minimal such that the I'm sorry, I don't know what's going on here. Such that the minimal length L of Kn of a braid whose closure is Kn grows faster, strictly faster than a constant times n. And my current expectation is that you should be able to find such a family which grows like, in which the minimal length grows like n to the 3/2. But I don't actually have an example. Okay. So that was comment number 1. And here is an odd comment. So there are actually, so you know, there are the Ridermeister moves. So there is this Ridermeister move, there is that Ridermeister move, and there is this Ridermeister moves. Okay? And I have nothing to say about this one. No comments. However, these Ridermeister moves actually come in 2 variants. When I draw it schematically, I don't bother to indicate the orientations of the strands. Okay? So I really mean allow these moves with all possible orientations. Okay? But you can split these moves according to the orientation. So for this move, for Ridermeister 2, the strands could be both oriented up, or one could be oriented up and one could be oriented down. If it's the second case, then the loop in the middle, right here in the middle, there is a closed domain, and this closed domain is oriented in a cyclic manner. Right? If you follow the orientations, it's a cyclic. You get a cycle. So I will call this variant of Ridermeister move of Ridermeister 2. I will call it R2C for R2 with a cyclic interior. And so far it never mattered, so I never bothered to say it, but you can make this separation. However, here the interior is not, the inside domain is like not cyclically oriented. So I will call this type of Ridermeister moves, of Ridermeister 2s, R2B, because really the type of Ridermeister moves that you see here is exactly the type of Ridermeister moves that you see in Braids. So both strands are oriented up, or oriented the same way. So this, the B here stands for, it's a braid-like Ridermeister 2. Okay? But by the way, I'm not insisting that it will be embedded facing up. So, you know, even if it was embedded sideways, but the orientations were the same or downward, and both are, I would still call it a braid-like Ridermeister 2. Similarly, for Ridermeister 3. So, for Ridermeister 3, you can have either the cyclic case. So the cyclic case is when the internal triangle is makes a cycle. So there is a cycle here. Okay, and so this I will call R3C, and here so sometimes the orientations do not allow you to make a cycle. So for example, if it's oriented this way, then you have like a picture like this, but again, this is not a cycle. But this is exactly the type of pictures that you will see when you do a Ridermeister 3 in a braid. So I will call this R3B. Okay, so having said this, so now knot diagrams are divided into, Ridermeister moves are divided into two types. The B type and the C type, and the Ridermeister ones. Okay, so what is knot theory? So the space of all knots is equal to the space of all knot diagrams. So I mean, this is all knots, in fact all knots and links, and this is all diagrams, modulo Ridermeister 1, Ridermeister 2, B and C, and Ridermeister 3, B and C. Okay? But now I can define a new space, K prime. So these are knot prime. Okay? Modified knots. There are other modifications to knots, but this is one. Okay? So this will be the space of all diagrams modulo only, so R1 and only R2B and and R3B. This turns out to be the interesting one. You could do the same with C's, but it's not interesting. Okay? So, Markov's theorem, so Markov's theorem on braids implies that K prime contains a copy of K. Why? Because every knot can be written as a braid closure, and the relations between the braid closures, namely the Markov relations, you can check are all, so the third Markov move, the interesting Markov move is just a Ridermeister 1, and all the other relations are B-type. So Markov theorem implies that K prime contains a copy of K, namely those knots that are braid closures, that are presented as braid closures. Okay? But it may contain more. So there are knots that so let me say two things. There are elements of K prime that are not braid closures, in as much as I know. Okay? So the Alexander algorithm, if you go back and look at it, uses both B and C type moves. So it doesn't work in K prime, it only works in K. Okay? So that's one point. And the second point is, in principle, it means that there are new ways to construct knot invariants. You could construct a knot invariant by just verifying invariants under the B moves. Okay? So if you regard knots as braid closures, you may have more invariants because there is less to verify. There are fewer cases to check. And I know exactly one invariant that is defined this way. Sort of, it's intrinsically an invariant of braid. It's defined by its invariant only under the B moves, and that makes it an invariant of knots by embedding K into K prime. In principle, there could be more, but I know only now one example. I know just one example where this is useful. So why did I tell you all of this? Because these are ground level, these are problems you can ask on day one of, very early on, and where I don't really understand anything. So I don't really understand what is K prime. I don't really understand if there is how big are the invariants of K prime don't automatically satisfy the Ridermeister, the C moves. And going back to the previous question, I don't know how lousy is the embedding or is the map from knots to braids. Okay, or how lousy, I don't know this very basic fact about n and n to the 3/2. Okay, so if you want to go home and think and and solve some open problems in knot theory, you may. Okay. I don't have any practical thing to say about it. I just wanted to introduce it. Okay. Questions, comments? Yes, Leonard?
Does the knot complexity has something to do with invariants? Like how difficult to find invariants?
No, it has to do with how difficult it is to compute an invariant. Right, so I don't know how hard it is to compute the Jones polynomial. Okay, but I don't know how hard it is to find the Jones polynomial, But once you found it, once you define the Jones polynomial, in order to compute it, you need approximately, well, and I'm being loose, and there are ways to improve, but at least if you're naive, you need 2 to the n smoothings. You need to consider 2 to the n smoothings. And the bigger n is, the more complex it is. If you present your knot as a braid, as a closure of a braid, you're going to need 2 to the n to the 3/2 computations, and that's a lot more. Okay? So usually it's inefficient to compute invariance by restricting your attention to braids. I mean, often people say braids are simpler, let's work with just braids, because all orientations are the same. So often people use braids to make explanations simple, but they pay by making computations a lot harder. Okay. Yeah, so I want to go back to braids. And of course I'm not going to get to the place where I comb braids today, because this turned out to take a long time. So first of all, there is an obvious map from the braid group to the symmetric group. Namely, every braid induces a permutation. If you have a crossing, you map it to the permutation. Okay? So the sigma i's of braid theory become the transpositions in the permutation group theory. Now, this map is surjective, so I'm using exact sequence notation. This is an exact sequence where 1 is the group with one element, because this map is surjective, because clearly you can find a braid for every permutation. Okay? Just turn all the crossings to overcrossings, to positive crossings. Right? I mean, okay, I'm wasting your time. So this map is surjective, but it has a kernel. The kernel is often called PBN, so to say that it's a kernel means that this whole sequence now here is exact. Okay? And what is PBN? So PBN are so-called pure braids with n strands. And what it means is that these are braids that induce the identity permutation. And if you want a picture of one, then for example, so e.g., take this braid. Okay, so this is really sigma 1 squared. So it's twice a positive crossing, and as a permutation it's the identity permutation, but as a braid it's non-trivial. Okay? By the way, there is also a pi1 description. So remember, braids were pi1 of the configuration space of n points where you modded out by the symmetric group. So modding out by the symmetric group just means that when you end your motion in configuration space, you want to return, all points have to, all n coordinates, all on n points have to return to where they were, but perhaps permuted because I've modded out by the symmetric group. So, so that would be an element, so this thing here would be an element in pi 1 of Cn tilde. Pure braid group, the pure braids are simply pi 1 of Cn without modding by the symmetric group. So in a way they're even simpler. They have a simpler description. It's actually a bit harder. You can write them as generators and relations. It's a bit harder and I will not do it. But I wanted to emphasize, sorry, so now I wanted to make two comments. So, studying BN and PBN is more or less the same, and I'm being informal here. So basically, suppose you have two elements of Bn and you want to decide if they're the same. Okay? If they induce different permutations, they're obviously not the same. Right? Otherwise, you take the first one and you multiply it by the inverse of the second, and at permutation level, you've multiplied a permutation by its inverse, because now I'm doing the case where they induce the same permutation. So at permutation level, you've multiplied a permutation by its inverse, so you got the identity permutation. So deciding if they're the same is a question about pure braids. So analyzing Bn and Pbn is more or less the same. Okay. Yet I should emphasize that yet this sequence, maybe I should give it a name, let's call it star. So this sequence star does not split. So what does it mean for a sequence to split? It means an exact sequence is called split if there is a map from a short exact sequence is called split if there is a map from the last thing to the second to the last thing, a homomorphism of groups, such that following this map and then going this way is the identity. So in other words, there is no map from Sn to Bn which covers the identity map, which such that the identity is such that the composition is the identity. So you will say, well, but this contradicts the fact this contradicts what I said before, that this map is surjective. So I mean, for every permutation, take a braid which is its pre-image. So you can do that, but this will be a set theoretic map, not a group theoretic map. It will not be a group homomorphism. For example, if you take this braid to be, for example, if you take this braid to be the image of the transposition, then, well, the transposition square is the identity, but this square is not the identity as I've shown here. So it's not a split, so it's not a group homomorphism. Okay? So such a purple map does not exist in the world of groups. Now, why is this significant? So I'm going to lie to you. I don't want to tell you why is it significant, because I actually want, the next few sentences I want to say them for another reason, not to explain why that was significant. Okay? But still, okay? So I want to make a short aside. So an aside on split exact sequences. So what does it mean? What means to have a splitting? So suppose you have an exact sequence, 1 goes to A, goes to B, goes to C, goes to 1. This is in the category of groups. And suppose, let's give the map's name. So this is usually called the inclusion, this is usually called a projection. And suppose there was a splitting, let's call it S for splitting. So what means a sequence like that, where, what was the condition again? S followed by P is the identity. So P circles S is the identity. I think I told you that I like to write it as S followed by P. Okay, but it doesn't matter. That's just my liking. So what does it mean in group theory? It means the following. Okay. First of all, even before the splitting, So it means, let me write it as 0. It means B contains a copy of A, that's automatic. Namely, you apply I to A, the image is a copy of A, since I is injective. So B contains A, or strictly speaking, B contains IA. Okay? But now that I have S, I know that B also contains a copy of C, a group theoretic copy of C. So B contains C, and again, strictly speaking, B contains SC, which I will identify with C. Now, I claim that in this case, B is equal to A times C. But this is like the subset A multiplied by the subset C. Okay? This is not, I'm not claiming that this is a product of groups. Okay, so I mean, I'm not saying B is equal to A cross C, because this is false. Okay? I'm only saying that the set A multiplied by the set C is the set B. Proof. I don't know. Suppose you have an element B in B, and I want to write it as A times C. The C part is clear. It must be PB. So you set lowercase c to be PB, and then you ask yourself, is it true that B is equal to something in A times S of PB times S of P of B? Well, that thing in A, whatever it is, let's call it alpha, because I don't know yet that it's in A, so I will not honor it with a Latin letter. I'll just give it a Greek letter. Sorry, this is not a racist statement. Okay, I'm just anyway. So alpha will be B multiplied by SPB inverse. I have to check if it's in A, right? To honor it and make it Latin, I'll have to check if it's in A. But to check if it's in A, I just need to check if it's in the kernel of P. I mean, to check if it's in A really means to check if it's in IA. And for this, I just need to check if it's in the kernel of P. So I compute P alpha, and this relation, everything cancels. You use everything and you get that this is the identity. So alpha really is an A. So alpha is in IA, and we're done. Okay? I'm almost out of time. I will go another minute. I'm sorry. So property, the next thing is that A is a normal subgroup of B, but that's obvious because A is the kernel of a map, right? This is as A is really the kernel of P, and kernels are always normal. And if you go back to algebra, to when you took algebra, whatever it was, you'll see that whenever a group B is presented as a product like that, and A is normal, it means that B is actually a semi-direct product. So B is equal to A semi-direct product C. And that was the conclusion I wanted to get, and it's not true, so it is false that braids are equal to pure braids semi-direct product permutations. So this is false because there is no splitting. However, I will use this the next minute of next class in a different context, in a different way. Okay? So, yeah, questions, comments? Sorry, I'm a minute and a half late.
Yes, so back to the complexity thing I said. The complexity of the braid and of knots. Yeah. So that of braid is quite higher than that of knots, but then when we look at the moves that you presented, the moves in braids are less than that in knots.
Yes.
So is
there are fewer moves to check.
Come again?
There are fewer moves to check if you're dealing only with braids.
Okay, so does that mean I'm studying braids
so
like
studying braids as means to study knots. If you want to study knots by studying braids, it's easier for humans and harder for computers.
Oh, I see.
Okay? It's easier for humans because you have fewer moves to check when you want to prove that something is an invariant. It's harder for computers because to compute things you actually need to first, you end up looking at longer braids. Okay? So, who do you care about more? Well, I don't know. Believe it or not, I tend to care more about computers because, you know, at the end of the day, I want to compute things. So, I mean, if I work a week longer and my invariant becomes defined even on becomes invariant even on relative to Ridermeister 2C and 3C, I worked a week longer, but now I can compute bigger things. So you know, I suppose I'm a traitor to my species. Okay. See you on Friday.
Yeah.